Hello, in this video we'll be learning about the chain rule. Let's start by talking about notation. Suppose we have an equation in the form y equals 2x plus 3. This is a linear equation, and so we know it has a constant rate of change. The slope for this equation is 2. And we can define slope in a number of ways. One way you're used to describing slope is the change in y per change in x. And in calculus, that delta y over delta x we can denote as dy over dx. And in this particular example, that value is equal to 2. And that means that as x increases by 1, y increases by 2. So this number 2, this slope, it tells us the change in y with respect to the variable x. It tells us how much y is changing as x increases by 1 unit. So when we read this notation out loud, we say the derivative of y with respect to x. It's the change in y with respect to our independent variable x. But if our equation isn't written using the variables x and y, we can still talk about the slope and we can still use this derivative notation. We just have to write it using the correct symbols. So let's say, for example, our equation was w equals 2t plus 3 instead. Well, my slope is still 2, but I wouldn't write dy dx. For this equation, I would say that my slope is equal to the change in w over the change in t. In other words, it would be dw dt, and I would say that it's the derivative of w with respect to t. Now let's practice using our Leibniz notation to express the derivative of each of the following functions. Number 1, since the equation is y equals 3x squared, our dependent variable is y, our independent variable is x, our slope is going to be the change in y with respect to the change in x. So it's going to be dy dx. And we can find this derivative using our power rule. So dy dx equals 6x. Number 2, w equals tan theta. W is my dependent variable, theta is my independent variable, so my derivative, or my slope, is going to be described as dw d theta. And the derivative of tan theta with respect to theta is secant squared theta. Number 3, s equals 2 to the power t. My dependent variable is s, my independent variable is t. So we have our derivative ds dt. And the derivative of 2 to the power t with respect to t is 2 to the power t times the natural log of 2. Number 4, u equals secant x. My derivative is going to be du over dx, so the derivative of u with respect to x. And derivative of secant x with respect to x is secant x tangent x. Number 5, y equals e to the power u. So my derivative will be dy du, and the derivative of e to the u with respect to u is e to the u times the natural log of e. The natural log of e is just 1, so our derivative simplifies to e to the power u. Next, we're going to practice identifying composite functions. So we're given several sample functions, and we're asked, is the function a sum, a product, a quotient, or a composite of basic functions? For the ones that are a composite, we're going to write down what is the inner function, what is the outer function, so that we can write the composite in the form f of u. If it's a sum, product, or quotient, we're going to go ahead and use the derivative rules we already know to find the derivative. Part A, h of x equals the tangent of 2 to the power x. This is a composite function. If I'm applying an operation to anything other than just plain old x, then we're going to think of it as a composite function. We're not taking the tangent of x, which would be like our parent function. We're taking the tangent of something else. In this case, we're taking the tangent of 2 to the power x. So 2 to the power x is my inside function. That's my something else. And then tangent of something is my outside function. So we're going to identify the inside function. We're going to call that u. In this case, I'm taking the tangent of something else. And by something else, I mean something other than just x. So my something else, my u, equals 2 to the power x. That's my inner function. And since 2 to the power x equals u, now I can replace 2 to the x with a u. And so this outer function now becomes the tangent of u. But we can't call that h because we're changing. It's not the tangent of 2 to the x anymore, so it's not h of x. We have to call it something else. So we're just going to call it f. And then f is going to be the function tangent of u. So in function notation, that would be written as f of u equals tangent of u. So we substituted u in place of 2 to the power x. And the reason we're separating our inner function from our outer function is because we don't have a derivative rule for taking the tangent of something else. We only have a rule for taking the tangent of x, or in this case, u. I mean, we can call the x whatever we want to call it as long as it's just a singular variable. So we know that the tangent of u is secant squared u. Our derivative rule tells us that. But the derivative rule does not tell us what is the tangent of 2 to the power x. So we're separating this into inside function, outside function, because hopefully we know how to find the derivative of each one of those parts. So we know the derivative of tangent u is secant squared u, and the derivative of 2 to the x is 2 to the x ln 2. And we still have to learn how these are related to each other, how we put them together to get the derivative that we're looking for. But for right now, we're just trying to identify these composites. Part B, p of x equals 2 to the x tan x. Now, 2 to the x isn't really inside anything in this function, and tan x isn't inside another function either. So this is just a product of two functions. And we have a product rule that will help us find this derivative. If we use the product rule, we get p prime of x equals derivative of the first, so I want the derivative of 2 to the power x, which is 2 to the x ln 2, times the second, so times tan x, plus the first, 2 to the x, times the derivative of the second, and derivative of tan x is secant squared x. So I was able to find the derivative of p using my product rule and my rule for tangent and my exponential rule. Part C, r of x equals tan x squared. This is a composite function. It's something else squared. It's not just plain old x squared. It's something else that's being squared. So that something else is my inner function. Tan x is my inner function here. So we're going to call the inner function u. U equals tan x. That's the thing that's being squared in this case. So my outer function is that something squared. So I'm going to write f of u equals u squared. The tan x is equal to u, so we can replace that with a u, and then this just becomes u squared. And again, if we look at these separately, we have derivative rules for finding the derivative of tan x. We have a derivative rule for finding the derivative of u squared. We don't have a specific rule for finding tan x squared. So we need to separate them out so that eventually we'll see how to use the chain rule to find this derivative. Part D, m of x equals e to the power tan x. This is a composite function. It's not just e to the x, it's e to something else. And in this case, that something else is tan x. So we have e raised to the power of something other than just plain x. So our inner function u equals tan x. And then if we replace the tan x with u, then we have e to the power u. So that becomes my outside function, e to the power u. And we have a derivative rule for finding the derivative of e to the power u. And we have a derivative rule for finding the derivative of tan x. So again, we're separating these parts out because it's going to help us find the derivative once we learn chain rule. Part E, w of x equals the square root of x plus the tangent of x. Now, we already have derivative rules for finding derivative of square root of x and for finding the derivative of tan x. So this is just the sum of basic functions. We don't have to try and think of this as a composite of something. It's just the sum of two functions. So our derivative, w prime of x, equals the derivative of square root of x, which is 1 over 2 root x, plus the derivative of tan x, which is secant squared x. And part F, we have z of x equals square root of tan x. This is a composite. It's not the square root of x, it's the square root of something else. So our inside function is tan x. And then if we replace the tan x with a u, we get the square root of u for our outside function. F of u equals square root u. Now, once we've separated them into inside function, outside function, we see that we have derivative rules for finding the derivative of u and the derivative of f of u. Okay, so now let's talk about the chain rule. Let's consider the example y equals 2x plus 3 squared. And we want to find the derivative of y with respect to x. Well, one option would be to expand this function. So we could write this as y equals 4x squared plus 12x plus 9, and then find the derivative using the power rule. So y prime equals 8x plus 12. And if we wanted to simplify that, we could write y prime equals 4 times 2x plus 3. Well, another way we could approach this problem is to think of it as a composite function. So I start with y equals the quantity 2x plus 3 squared. And I have my inside function, u equals 2x plus 3. Since it's not just x that's being squared, it's something else, some other stuff that's being squared. My inside function is that other stuff that's being squared. The u equals 2x plus 3. And then I have my outside function, which is that stuff squared, u squared. If u equals 2x plus 3, then we can come up to the original function and replace the 2x plus 3 with u. So I get u squared as my outside function. Now let's consider the derivative of my inside function and the derivative of my outside function. My inside function, u equals 2x plus 3. If I take the derivative of 2x plus 3, I just get 2. But what is that the derivative of? Let's think back to our Leibniz notation. If this equation said y equals 2x plus 3, then 2 would be the derivative of y with respect to x. But it doesn't say y equals, it says u equals. So my derivative would have to be du over dx. The derivative of u with respect to x equals 2. And then if I want to take the derivative of u squared, now my independent variable here is a u squared. Well, we have to call this something. We need a name for our function if we're going to use Leibniz notation. So let's go ahead and call it y. Since y does equal u squared, I'm bringing that down from the original problem. Now if I take the derivative of u squared, I get 2u. But again, think about what is that the derivative of? That's the derivative of y, so it's dy. But it's not with respect to x, it's with respect to the variable u, so it's dy du. dy du equals 2 times u, using our power rule. But what I'm really interested in finding, the derivative of my original equation, the derivative that I want is dy dx, the derivative of y with respect to x. So I need dy dx, and what I've got is du dx and dy du. But if we take du dx and we multiply it by dy du, if we multiply these together, notice that the du's cancel out. And what I have left is a dy on top and a dx on the bottom. So if I want dy dx, what this means is that I just multiply du dx times dy du. And du dx, remember that was my inner function, And dy du, that was my outer function when I rewrote it with the variable u. So we're going to multiply derivative of inner times derivative of outer. And the derivative of my inner function in this case was 2 times the derivative of my outer function was 2u. And so my derivative of interest, dy dx, is equal to 4 times u. And if we go back to our original variable, u is defined up here as 2x plus 3. So 4 times u is really 4 times 2x plus 3. And that is the same answer we got when we found the derivative this other way. When we multiply the derivative of the outer function and the derivative of the inner function, that's what we refer to as the chain rule. Let's try this again with a new function, y equals 2x plus 3 to the power 7. So in the last example, we found the derivative two different ways. First, without using the chain rule, by just expanding terms and using the power rule, and then with the chain rule. And you might have thought the first way was easier. For that particular example, I would agree. It was easier to expand and use the power rule. However, in a problem like this, 2x plus 3 to the power 7 is much more difficult and time-consuming to expand. We can get our derivative a lot quicker if we use the chain rule instead. So remember, when we're going to use the chain rule, we have to identify what is our inside function and then what is our outside function. In this case, the inside function, my u, is 2x plus 3. And my outside function, when I replace the 2x plus 3 with a u, I get y equals u to the power 7. So that's my inside function and my outside function. And now we want to find the derivative of each one of those. If u equals 2x plus 3, then du dx equals 2. The derivative of 2x plus 3 is 2. The derivative of my outside function is dy du. And that's the derivative of u to the power 7. Using the power rule, that's 7 times u to the power 6. So now if I want to find dy dx equals du dx times dy du. So that's going to be my 2 times my 7u to the power 6, which gives me 14u to the power 6. And then we need to write our final answer in terms of our original variable x. So we replace u with what u is equal to in terms of x. So u is 2x plus 3 to the power 6. So that is the derivative of y with respect to x. For this next set of problems, we're going to identify the inside and outside functions. Number 1, y equals 3 times the quantity 6 minus x squared. So I'm seeing the 6 minus x as the inside function. That's the stuff that we're squaring. So I'm going to think of this as 3 times stuff squared, where the stuff is my inner function that I'm going to define as u. So I have u equals 6 minus x, and then my outside function, f of u, is 3 times u squared. 3 times stuff squared, in other words, is my outside function, 3u squared. Number 2, y equals the square root of 2x minus 1. This is not just the square root of x, this is the square root of other stuff. So this is in the form of square root of stuff. My inside function is this stuff. So u equals 2x minus 1 is my inside function. My outside function is square root of stuff, so square root of u, and we'll call that f of u equals square root of u. That's my outer function. Number 3, y equals 1 over 4x plus 1. Well, it's not just 1 over x, it's 1 over stuff. 1 over stuff. And what I'm trying to do with this writing with the stuff is to come up with something that we do know how to take the derivative of, something that we have a derivative rule for. And we have a derivative rule for 1 over x. In this case, we're going to treat the stuff as though it were an x. So if the derivative of 1 over x is negative 1 over x squared, then the derivative of 1 over stuff is going to be negative 1 over stuff squared, but then we have to use the chain rule to finish it by multiplying by the derivative of the stuff. But I might be getting a little bit ahead of myself here. For this problem, we're just trying to identify what's the inside, what's the outside. So my u, my inside function, is the stuff. That's the 4x plus 1. And my outside function, f of u, that's the 1 over stuff. So 1 over u. Number 4, y equals the sine of 2x. So this is y equals the sine of stuff. The stuff being my inside function. So u equals 2x. 2x is my inner function. And then f of u equals, sine stuff is sine of u. My outside function is sine of u. Number 5, y equals cosine cubed x. Now here we want to rewrite this as cosine of x, that quantity, cubed, so that we can identify what's the inside function. This is stuff cubed. This is in the form of stuff cubed. So my inside function is the cosine x, and my outer function, f of u, is u cubed, the stuff cubed. Number 6, y equals cube root of x squared plus x. So this is the cube root of stuff, stuff being my inside function. So u equals x squared plus x, that's my inner function, and then f of u equals cube root of stuff, or cube root of u, as my outside function. Okay, so the chain rule tells us that if h of x is a composite function, if h of x equals f of g of x, then the derivative of h with respect to x, so h prime of x, is equal to f prime of g of x times g prime of x. F prime of g of x here is the derivative of our outside function, times g prime of x is the derivative of our inside function. So we just take the derivative of the outside function times the derivative of the inside function. If we look at this in Leibniz notation, same thing, dy dx is equal to the derivative of the outside function, that's our dy du, times the derivative of the inside function. The inside function is our du dx. So think chain rule whenever you have a composite function. If it's a function of not just x, but of some other stuff, remember, the derivative of f of stuff equals f prime of stuff times the derivative of the stuff. So f prime of stuff, that's your outside function, derivative of your outside function, and then stuff prime is the derivative of the inside function. Okay, let's practice. So number 1, y equals 2x plus 3 to the power 15. We want to find dy dx. So dy dx equals. Now, when I see this, I'm thinking to myself, this is stuff to the power 15. So my derivative is going to be 15 times the stuff to the power 14 times the derivative of the stuff. And the derivative of the stuff, and I'm talking about the derivative of 2x plus 3, is 2. So this is equal to 30 times 2x plus 3 to the power 14. Number 2, y equals the sine of x squared plus 5. So here my inside function, or my stuff, is the x squared plus 5. So if this is y equals sine of stuff, then my derivative, dy dx, is the derivative of sine of stuff. The derivative of sine of stuff is cosine of stuff, so cosine of x squared plus 5, times the derivative of the stuff, and the derivative of the stuff is 2x. So 2x cosine x squared plus 5. Number 3, y equals sine of cosine x. So here my inside function is cosine x. Cosine x is the stuff. So I want the derivative of sine of stuff, and the derivative of sine of stuff is cosine of stuff times the derivative of the stuff, and the derivative of cosine x is negative sine x. There's not much we can do to simplify that. I can take the negative 1 out front, so it's negative let's do it this way, negative sine x times the cosine of the cosine of x. Number 4, y equals e to the power 3x. So my stuff, or my inner function, is the 3x. So dy dx, I have e to the stuff. The derivative of e to the stuff is e to the stuff times the derivative of the stuff. So 3e to the 3x. Number 5, if dz dx equals 12 and dy dx equals 2, then dz dy equals what? Well, I want dz over dy. I have dz over dx. So in order to get dz over dy, I would need this dx to cancel out. So I can put a dx on the top, and I need a dy for the bottom. So dz over dx times dx over dy would simplify to dz over dy. Well, I know that dz over dx is 12 times, and I don't have dx dy, but I have dy dx, which is just the reciprocal of dx dy. So if dy dx is 2, then dx dy is 1/2, and 12 times 1/2 equals 6. Number 6, m of x equals e to the power 9x. So now we have functions that aren't defined in terms of x and y. We're calling them by other variable names. So let's practice our notation. I could call this dm dx, or I'm just going to go with this other notation, m prime of x, for my derivatives. So the derivative of m with respect to x equals, now this is e to the stuff, so it does require the chain rule. The derivative of e to the stuff is e to the stuff times the derivative of the stuff. So 9 e to the 9x. Number 7, h of x equals cosine of x to the 4th. So h prime of x, I'm going to need chain rule here as well because this is cosine of stuff. The derivative of cosine of stuff is negative sine of stuff times the derivative of the stuff. And the derivative of x to the 4th is 4x cubed. So we simplify this, we get negative 4x cubed times the sine of x to the 4th. Number 8, p of x equals the square root of tan x. P prime of x, we need the chain rule here because this is the square root of stuff. So the derivative of square root of stuff is 1 over 2 root stuff times the derivative of the stuff. And the derivative of tan x is secant squared x. So we can write this as secant squared x over 2 times the square root of tan x. Number 9, s of x equals 2 to the power sine x. So s prime of x, we need chain rule here because it's 2 raised to the power stuff. So the derivative of 2 to the power stuff is 2 to the power stuff times the derivative of the stuff. And the derivative of sine x is cosine x. Oh, and I forgot my times the natural log of 2. Let's try that one again. So the derivative of 2 to the power stuff is 2 to the power stuff times the natural log of 2 times the derivative of the stuff. And the derivative of sine x is cosine x. Number 10, z of x equals cotangent of x to the power 5. So I'm going to think of this as cotan x all raised to the power 5. So now I can see that the outside function is stuff to the power 5. So now z prime of x, the derivative of stuff to the power 5 is 5 times stuff to the power 4 times the derivative of the stuff. And the derivative of cotan x is negative cosecant squared x. So this is negative 5 cosecant squared x cotan to the power 4 x. For this next problem, we're going to use the derivative rules that we know, now including the chain rule, to answer each of the following questions. Part A, find an equation for the tangent line to the curve y equals square root of e to the x plus 3 at the point where x equals 0. To write the tangent line equation, we need to know two things. We need to know the value of y when x is 0 and the value of y prime when x is 0. So let's start by finding the value of y when x is 0. Y of 0 equals the square root of e to the power 0 plus 3. E to the power 0 is 1, so e to the power 0 plus 3 is 4, and the square root of 4 is 2. That gives me my point of tangency at 0, 2. So 0, 2 is my point of tangency. Now let's find the value of y prime at 0. So y prime, to find that derivative, y is equal to the square root of stuff. So the derivative is going to be 1 over 2 root stuff times the derivative of the stuff. And the derivative of the stuff is e to the x. So now we want y prime of 0. Y prime of 0 is going to be 1 over 2 times the square root of e to the power 0 plus 3 times e to the power 0. E to the power 0 is 1, so this gives us 1 over 2 times 2 times 1, or 1/4. So now we can use that as the slope of our tangent line, and our equation of the tangent line when x is 0 is y minus 2 equals 1/4 times x minus 0, or just x. Suppose that f of x and u of x are differentiable functions and that the following information about them is known. So we have a table showing values of f, f prime, u, and u prime when x is -1 and when x is 2. If c of x is given by f of u of x, determine c prime of 2. So first we find c prime of x. The derivative of c prime of x is the derivative of f of u of x. So it's f of u of x prime. And this is a composite function, so we have to use the chain rule. The derivative of f of u of x is f prime of u of x times the derivative of the inside, so times u prime of x. Now we want c prime of 2. So c prime of 2 is going to be f prime of u of 2 times u prime of 2. And from the table, let's get u prime of 2. U prime of 2 is equal to 2. And then u of 2, so right here, u of 2 is equal to -1. And then that means we need f prime of -1. F prime of -1 is -5. So this is -5 times 2, or -10. If d of x is f of x, find d prime of -1. So d of x equals f of x. D prime of x is going to be the derivative of f of x. And this is a composite function, so it's the derivative of the outer function, f prime of f of x, times the derivative of the inner function, f prime of x. We can still think of this as the inside function being the stuff. If we do that, f of x has f of x as the stuff. It's f of stuff, so we take f prime of stuff times the derivative of the stuff. And we want d prime of -1. So d prime of -1 now equals f prime of f of -1 times f prime of -1. Okay, so let's start here this time. F of -1. F of -1 is 2. So I need f prime of 2. F prime of 2 times f prime of -1. F prime of 2 equals 4, and f prime of -1 equals -5. 4 times -5 equals -20. All right, let's finish up our chain rule lesson with some more challenging examples. So we've got 5 more problems to work through. Number 1, p of r equals 4 times the square root of r to the power 6 plus 2e to the power r. I want to find p prime of r, or dp dr. My inside function is r to the power 6 plus 2e to the power r. That's my stuff. This is in the form of 4 times the square root of stuff. So for those of you who like to write down your inner function, we can do that over here as an aside. U equals r to the power 6 plus 2e to the power r. That's my inner function. And then my f of u equals 4 square root u. That's my outer function. So we have to take the derivative of each of these and multiply them together. Or what I prefer to do in my head when I'm working this out is to say this is 4 times the square root of stuff. And I know that the derivative of square root stuff is 1 over 2 root stuff times derivative of stuff. And then we're just multiplying it by 4. So it's 4 times 1 over 2 root stuff times the derivative of the stuff. So the derivative of the stuff is 6r to the power 5 plus 2 times e to the power r. And we can do a little bit of simplifying here. I've got this 4 divided by this 2 is just going to leave me with a 2 in the numerator. And if I wanted to, I could factor out a 2 here, leaving me with a 3 and a 1. So bringing another 2 out. So I get 4 times 3r to the 5th plus e to the power r all over the square root r to the power 6 plus 2e to the power r. So that's the derivative of p with respect to r. Number 2, m of v equals sine of v squared times cosine of v cubed. So I have a couple different inside functions here. We're going to have to use a multiple use of the chain rule for this problem. My outermost function is sine of stuff times cosine of stuff. Unfortunately, it's not the same stuff. It's different stuff. So we're going to have to do chain rules separately here. But I'm going to go ahead and start taking the derivative of my outer function using the product rule. Okay, so I'm thinking of this sine of v squared as my first factor, and then cosine of v cubed as my second factor. So product rule, we want derivative of the first factor. The derivative of sine of stuff is cosine stuff times the derivative of the stuff. Okay, that's just the derivative of the first. So product rule says take derivative of the first times the second. So I'm multiplying that by the cosine of v cubed plus the first, so sine of v squared, times the derivative of the second. And when I go to take the derivative of the second, this is the cosine of stuff. So the derivative of cosine stuff is negative sine stuff times the derivative of the stuff, 3v squared. And we'll simplify this a little bit. We'll move our coefficients to the front. So I've got 2 times v times the cosine of v squared times the cosine of v cubed minus 3v squared times the sine of v squared times the sine of v cubed. Number 3, h of y equals cosine of 10y over e to the 4y plus 1. So here I'm going to use the quotient rule to start. I'm going to need chain rule when I take the derivative of the top because it's cosine of stuff. But I'm also going to need chain rule when I take the derivative of the bottom because it's e to the stuff. And again, they're different stuffs, but if I do this slowly, I should be able to keep it straight in my head. So I'm going to start out using quotient rule. H prime of y equals. So for quotient rule, we want to take the derivative of the top. The derivative of cosine stuff is negative sine stuff times derivative of the stuff. So that's just derivative of the top right there, times the bottom. So e to the 4y plus 1 minus the top cosine of 10y times the derivative of the bottom. The derivative of the bottom, I'm taking the derivative of e to the stuff plus 1. So the derivative of e to the stuff is e to the stuff times the derivative of the stuff. And then the plus 1 just becomes plus 0. All of that over bottom squared, e to the 4y plus 1 squared. And then to simplify, I'm just going to rearrange terms a little bit, move my coefficients to the front. So I get negative 10 times the sine of 10y times e to the 4y plus 1 minus 4e to the 4y times the cosine of 10y all over e to the 4y plus 1 squared. Number 4, s of z equals 2 to the power z squared secant z. So my outside function is 2 to the power stuff. My inside function z squared secant z. So we start by taking the derivative of the outside function. The derivative of 2 to the power stuff is 2 to the power stuff times the natural log of the base, so natural log of 2, times the derivative of the stuff. And the derivative of the stuff requires product rule. So product rule, derivative of the first, my first is z squared. So derivative of the first is 2z times the second, secant z, plus the first, z squared, times derivative of the second. The derivative of secant z is secant z tangent z. And there's no way we can really simplify that, so we'll leave our answer in that form. And our final example, c of x equals sine of e to the x squared. So our outside function, this is sine of stuff. So we start by taking the derivative of our outside function. Derivative of sine stuff is cosine stuff times the derivative of the stuff. The derivative of e to the x squared. Well, this requires another chain rule because this isn't just e to the x, it's e to the stuff. So the derivative of e to the stuff is e to the stuff times the derivative of the stuff. And the derivative of x squared in this case is 2x. So this is a double chain rule problem. And we can rearrange terms a little bit. This would be 2x e to the x squared times cosine of e to the x squared.